Hi, I'm Brooke Bobo, and this is my video for Organic Chemistry 1, Week 15 of solving a combined spectral problem. So my given formula for this assignment was C6H12O2, and before you can even look at the IR, HNMR, and CNMR spectrums, you can actually get a good bit of information just from the formula. So just from this, I know that there are 6 carbons, 12 hydrogens, and 2 oxygens, obviously, and this makes me think, my outcome of this, like my final product, is probably going to be a carboxylic acid or an ester, because those are the 2 biggest functional groups that have 2 oxygens in them. So I'm probably not going to have an aldehyde or just a plain ketone or an alcohol or anything, or especially not an amide or anything like that, because I don't have any other alkyl halides or anything. Like, I don't have any halogens or nitrogens, and I know I'm just working with carbons, hydrogens, and oxygens, which narrows down my functional groups a lot to try to figure out what I'm looking for in my spectrums. So the first thing that I looked at was the IR spectrum, and what you can see here from the beginning, the first thing I picked out was at the 1700 range right here that I'm circling, and that's very clearly a carbon-oxygen double bond, which lines up with what I talked about earlier about there being 2 oxygens in my formula. And then around 2900 here, you can see the sp3 carbon-hydrogen stretches, which shows that all my carbons are going to be bonded to 3 other things. There's not going to be any double bonds of carbon or anything like that, because there's no sp2 carbons anywhere in the spectrum. And then finally around 1200 here, you can see the peaks of around all of these from the carbon-oxygen bond, and that's telling me that this is going to be an ester as opposed to a carboxylic acid, which was kind of what I had narrowed it down to just from looking at the formula. The next thing I did was calculate my degrees of unsaturation. So this can be done by taking your chemical formula, which, as I said earlier, was C6H12O2, and what you're going to do with that is multiply the number of carbons you have by 2, so 6 times 2 is 12, and then you add 2. That gives you 14. Well, that kind of means I should have 14 hydrogens, but I only have 12, so I would divide that number by 2, the 2 by 2, because I have 2 more, or 2 less, I have 12 as opposed to 14, and then divide that by 2 to get 1. So I have 1 degree of unsaturation, which means that there will be 1 double bond or ring in my structure, and that lines up perfectly with the 1 double bond we had, the carbon-oxygen double bond. The thing I looked at after that was my CNMR spectra, and what you can see here, the big thing that jumps out to me just starting off looking at it is around 170 here, this peak. This is just shifted so far to the left of the spectrum, and it's showing you that it is a carbon that's bonded to a very electronegative atom, and this is what I attributed to the carbon double bonded to the oxygen. So that definitely is poking out there. And then also these really 2 close ones right here. I know it's 2 even though it kind of looks like 1 because I have 6 carbons, so there would be 1, 2, 3, 4, 5, 6 right there. And this one right here around 52 is what I approximated it to be at. That's going to be the carbon that's bonded to the oxygen, because it's also shifted the furthest to the left of the spectrum that we're looking at. And then all the other ones would just be normal sp3 carbons bonded to 3 other things. And then finally, the last thing I looked at was my HNMR spectrum. Now, the HNMR can give you a lot of information, so it's really important that you read into everything. Starting off with this first peak down on the far left of the spectrum that I'm kind of circling right here, this one is given an integration of 3 hydrogens. So we know that these 3 hydrogens are all attached to the same thing. It's a singlet, so that means it doesn't have any neighbors, so there are no hydrogens neighboring it. So I attributed that to be a CH3 that is bonded to an oxygen. So that leads me to believe that on my ester, on the single oxygen bond, coming off of that is a CH3 group. So that means all the other carbons are going to be on the other side of the ketone part of the ester. So then I moved on down to the next one that I'm circling right now. There are 2 hydrogens in that one. That's what the integration value is, and it's a doublet. So that means there will be 1 neighbor. So these hydrogens have to have neighbors that are only 1 hydrogen. So it has to be like a CH2 group, since there's 2 hydrogens, bonded to just a CH. So what I attributed that to, as you can see over here, is that CH2 group is probably bonded on one side to the oxygen that the CH3 group that was mentioned before is bonded to, and on the other side is bonded to a CH group. And then I moved on down one further, and I saw this multiplet, which I kind of looked at really closely. I zoomed in on it in my computer whenever I was attributing these, and I counted that out to be a sextet, so it would have 5 neighbors. And I looked and saw that this one is 1 hydrogen with 6, or it would be a septet, I guess. What, it's 5 or 6. If it's a multiplet, it's kind of hard to see. So I kind of assumed it would have 6 neighbors, so it would really be a septet, I guess. And that would mean that there was a CH carbon with 1 hydrogen that is bonded to 2 CH3 groups, which would line up with, right on the next peak here, we have 6 hydrogens, and that's a doublet. So that means it only has 1 neighbor, so this could be the 2 CH3 groups that were bonded to that first CH group, the last thing I mentioned. So with all this information in mind, I added it all together, drew up a little structure, and double-checked it, went back with all of my different spectrums that I had before, and made sure it made sense, and this was the proposed structure that I got, this ester right here. So this proposed structure is what I think that my spectral analysis would have been the result of this, and that was my reasoning for it. Thank you.